you have point B. And then we have the load exactly on the center. Okay. And this is our P in the Y, right? So if I would draw our transformation, so X, Y, and then we have our rotation in the Z. Okay. So we know, and this is our point C, already now we know that the structure will fill at point C. Okay. And one thing I want to highlight, the distance from here to here, and the distance from here to here. Right. So this is our L/2, our L/2. So this is our simply supported beam. The next one I'm going to draw. Okay, so this is why sometimes for this case, right, when the loading is exactly at the center. Okay, when the loading is exactly at the center, means the loading is at what? L/2. The entire beam is L. Okay, so this is equivalent to this. Okay, so now I'm going to draw the other side now. Okay, and then the beam now is half the L/2. Yeah, try to do half. Hey, sometimes the computer don't listen to me. Oh, now I make things worse for myself. My bad. Okay, sorry. So now this is our cantilever beam now. Okay. So now this is a cantilever beam. Okay. Before I go on, we know that at point A we have a reaction force. Okay, so this is P/2, right? And point B we have a reaction force. This is P/2. Okay. When this is the case, okay, on the cantilever beam, I can also put this as P/2. Okay, and the distance from here to here is L/2. Okay, so this is my point A, and this is my point C. And as I mentioned before earlier, failure will occur at where? At point C. Now, question for you: where will failure occur at? Point A or point C? Anyone? When it's a cantilever beam. Okay, so this is our cantilever beam. Right? Failure will occur at point C. Yeah, absolutely right. So over here, the failure will occur at point C. Okay, right? Because if you don't believe me, okay, you just take a ruler and point C is your finger. Okay, you grip your ruler really tight, and point A is where you push your ruler. Right? Your ruler will break at where? Will break at point C. Okay, that is how I like to illustrate. So now, if we were to draw, okay, if we were to draw the shear force, okay, if we were to draw the shear force, and bending moment, not draw, but we're going to come up with the shear force and bending moment equation first. Okay, don't worry about this yet. Okay, I have not taught you this yet. Okay, but it's not that difficult. Okay, so now we are going to form the equation. So this is 0. So the limit is 0 to x to L/2. So this is between point A to point C. Okay, so from A to point C. Okay, so this is our beam. So this is our point A. We know point A, we have P/2, right? So this is our distance X now. Okay, and then we assume the shear force is coming down, V as a function of X, and then moment as a function of X. Okay, so we're going to apply static analysis. Okay, we're going to apply static analysis. Positive is going up, summation of forces in the y direction is equal to 0. We have P/2 minus by V as a function of X is equal to 0. So V as a function of X is equal to P/2. Okay, so this is our shear force equation. And the shear force equation, the limits is 0 to L/2. Okay, and then if we form our moment equation, so we're going to do summation about moment in the z direction anywhere upon the variable x. Okay, so some of you will say, Eugene, where are we taking our moment from now? So the moment we are taking now is at the dot that I'm constructing now. Okay, you'll see the blue dot. There is where we are constructing our moment. Okay, so from here, what we have is P/2 multiplied by X, so it's minus, okay, minus P/2 X. Why minus? Because it's going in the clockwise direction. So plus by M as a function of X is equal to 0. So M as a function of X is equal to P/2X or Px/2. Okay, so sorry, I think I better write this as Px/2, or not you can get confused. Okay, so this is Px/2. Okay, so now if we were to construct our shear force and bending moment, so this is our bending moment equation. We will learn more of this after your term test 2. Okay, a lot more. Okay, we can handle, we're going to calculate the load distribution in more complex loading situation than this. Okay, this is simple stuff. So if we were to draw our shear force diagram now, okay, so this is V, this is X, at this point is L/2, and then we have L. Okay, so this is our point A. Over here is our point C, and this is our point B. Right, so what you'll see is you are going to have a line coming from here to here, and then the line will stop here. Okay, so this is where we have our positive P/2 from A to point. So it's a constant line, because if you look at the equation, this is P/2 is constant. Then at a point C, you have a force P acting downwards. Okay, so at point C, you have a force P acting downwards. And at this point, it will stop at, okay, minus P/2. And then it will then move horizontally. Okay. And then it will cover back. Okay. So what you see over here from 0 to L/2, you have positive shear force. Over here, you have negative shear force. Next, we are going to construct our bending moment diagram. Okay, and you can see this is px over 2. Okay, so the parent function, this is high school stuff, I hope you all remember. Okay, is equal to y is equal to mx plus c. Yes or no? So this is our linear function, linear gradient function. Okay, so when that's the case, you have our bending moment diagram. So this is moment now. Okay, and over here, this is our x-axis. I'll draw it lower. Okay, so this is our x-axis. Okay, so what we realized looking at the function over there. Okay, so this is our 0. This is our L over 2, right? And then this is our hold on, let me draw better than that. That is not our so our L over 2 is over here, and this is our point B. So this is our point A, point C, and this is our point B. And if you look at our gradient, okay, m as a function of x, or m as a function is px over 2, the normal stress will go up this way. Okay, and then once it reach L over 2, it will start to decline. Okay, you start to decline, and that point over there, that magnitude is equal to P over 2 multiplied by L over 2. The moment is PL over 4. Okay, so that is PL over 4. So what you see over here, from 0 to L over 2, you have positive. No, hold on. You have positive moment or bending moment. So not positive, positive gradient. Okay, it's a slope. Okay, and then from C to B, you have negative gradient bending moment. Okay, can someone tell me what is the relationship or what is the trend that you see in the bending moment diagram and shear force diagram? What can you relate? Anyone? Can you see two very similar things from 0 to L over 2 and L over 2 to L? Can you see anything that's similar? Can anyone tell me what is similar that you can see? Which will help you later on, okay, in constructing your shear force and bending moment diagram. Can you see anything very prompting? Observe. What can you see? Anyone? I hope yes.
From A to C, it's positive, and C to B, it's negative. For
Well
both.
done. Well done. Okay, just well done. So what it means, what it means is this, okay? When your shear force magnitude is positive, your bending moment gradient is what? Positive. When your shear force is magnitude is negative, right? Your bending moment gradient is negative. Okay, so I want you to observe this, because later on when you sketch your, or when you form your equation, it will help you to see whether the equation is right or wrong. Okay, so this is just I think you have learned this in colleges. If not, this is just a reminder. Okay, a reminder. Okay, so again, this will help you guys in probably week 9 or week 10. Okay, but you will need this for bending that we are doing now. Okay, you will need this. Okay, now we have been focusing a lot on simply support.